Hello friends, welcome to all. Myself Vishal Jogidas. Today we will discuss about single phase induction motor and this topic is covered in the subject of electrical machines too. Now first we will see introduction. Construction of a single phase induction motor is similar to the construction of the three phase induction motor. It means we have already seen the three phase induction motor. There are stator, rotor, and all these things are there. So this motor also having a squirrel cage rotor, except that the stator is wound for a single phase supply. Difference in this construction is that in a single phase induction motor the stator is wound for single phase supply, and in a three phase induction motor stator is wound for three phase supply. So this is the difference between single phase and three phase induction motor. Stator is also provided with a starting winding which is used only for starting purpose. This can be understood from the schematic of a single phase induction motor at the left. So in this diagram we can see stator, then in center there is a rotor and shaft, and two windings we can see. One is the main winding and another one is the starting winding. So starting winding is used for the purpose of starting purpose only. Whenever the motor is start and it is moving up to some speed, then starting winding will not comes into picture and only the working winding is main winding. So this is the principle or basics of single phase induction motor. Now this is the actual single phase induction motor. So this is the photograph of actual motor. In first photograph we can see stator. So here we can see in stator winding also, and inner surface we can also see there are some slots of stator. So this is the typical stator, and we can also see the winding is orange color type. So it means there are laminations are there on winding. Second figure is rotor. Generally squirrel cage type rotor is used in a single phase induction motor. Here we can see shaft. This one is the bearing. Two types of bearings available. One is ball bearings and another one is roller bearings. So any type of bearing can be used for this. So this is the construction of a single phase induction motor. Now construction is similar as that of three phase squirrel cage induction motor that we have already mentioned. A single phase induction motor has two main parts. We already know that one is stator and another one is rotor. Now first we will see stator. Stator is similar to three phase induction motor. It consisting of a steel frame that supports a hollow laminated cylindrical core. So it is made from steel. Frame of stator is made from silicone steel, and this is the construction about stator. And the core is cylindrical type. Laminated cylindrical core is there. Core constructed from a stacked laminations. See, we have also seen that there is a laminations. Why? What is the need of laminations? So this is the homework for you. You have to find why the laminations are there. Having a number of evenly spaced slots providing the space for the stator winding. We have also seen the number of slots in a stator. So this is the construction of stator. Now we can see the view of stator construction. So here we can see single phase stator winding in stator slots. Okay, this one is the stator slots. This is the stator teeth. Then outer periphery is frame or yoke. Okay, it is used for mechanical support. And then laminated core is there. So this is the construction of stator. Now another main part of single phase induction motor is rotor. So squirrel cage type rotor is used, and aluminum bus bars sorted together at the ends by two aluminum rings. This is known as end rings. This is also available in a three phase squirrel cage rotor. So in this case also there are two end rings, and it is sorted together using aluminum bars. Okay, so this is the schematic diagram of rotor. So here we can see this is the end rings, and this is placed in both sides. Here also one end ring, and here also one end ring, and here is this one is shaft, and aluminum or copper bars are there. This one are the aluminum bars, and these are sorted with these two end rings. Okay, so this is the typical construction. It is known as squirrel cage type rotor, and mechanical output of the motor will taken from shaft. Okay, so we already know all these things. Now constructional representation of rotor and stator. So here we can see windings, stator windings are there. Okay, here is a squirrel cage rotor, and single phase supply is given to the stator because it is a single phase motor. Here we can see in first figure there are single phase stator winding is there, then squirrel cage rotor is there in a center, and in the center there is a shaft. So this is the representation of single phase induction motor. Now shaft. So shaft is nothing but we will take a mechanical output of motor from the shaft, and it should withstand maximum braking strength because mechanical load will be on the shaft, so it should withstand this braking strength. Then bearings. So we have already mentioned that two types of bearings are there, roller bearings or ball bearings. So any type of bearing we can use. It is used in vacuum cleaner, then fans, washing machine, centrifugal pumps, blowers, washing machine, small toys, etc. So these are the typical applications of single phase induction motors. See, number of applications are there for single phase induction motors. Now working principle of single phase induction motor. When the stator of a single phase motor is fed with a single phase supply, it produces alternating flux in the stator winding. Okay, whenever the single phase supply is given to the stator, at that time alternating flux will produced in a stator winding. The alternating current flowing through the stator winding causes induced current in the rotor bars according to Faraday's law of electromagnetic induction. Whenever the alternating current is flowing from stator, according to Faraday's law of electromagnetic induction, in a rotor also there is a flux is produced. Okay, so this induced current in rotor will produce alternating flux. Even after both alternating fluxes are set up, the motor fails to start. Okay, both, see, we have already seen that both fluxes are set up, then also motor will not start. Why? However, if the rotor is given an initial start by external force in either direction, then motor accelerates to its final speed and keeps running with its rated speed. It means if we give the initial starting force in any direction, it means in a clockwise direction or in anti-clockwise direction, then motor will run on that direction, and it will pick up the speed. This behavior of a single phase motor can be explained by double field revolving theory. So from this discussion we can say that single phase induction motor is not self starting. Okay, we have to do some arrangement for the starting of the single phase induction motor. And why it is not self starting, it can be explained with the use of double field revolving theory. We will see also this theory in detail. Types of single phase motors. The single phase motor which are designed to operate from a single phase supply are manufactured in large number of types to perform a wide variety of useful services in home, offices, factories, workshops, and in a business establishments. So there are lots of applications are there for single phase induction motors, and a variety of designs are available in a market, commercial markets. Small motors, particularly in a fractional kilowatt sizes, are better known than any other. The single phase induction motors are generally small sizes, and these are uh, applications of single phase induction motors are also very small sizes motors. In fact, most of the new products of the manufacturers of space vehicles, aircrafts, business machines, and power tools, etc., have been possible due to the advances made in design of fractional kilowatt motors. Since the performance requirements of various applications after so widely, the motor manufacturing industry has developed many different types of such motors, each being designed to meet specific demands. Okay, so nowadays so many types and sizes motors are available, and it is designed for particular applications. So as per our requirement we can select the motor and we can use it. Single phase motors may be classified as under depending on their construction and method of starting. One is induction motors. In that case, there are split phase, capacitor, and shaded pole motors are there. Another one is repulsion motors, sometimes called inductive series motor. So this is also one type of motor. Then AC series motor, and fourth one is unexcited synchronous motors. So these are the types of single phase motors available. Now constructionally, this motor is more or less similar to the polyphase induction motor, except its stator is provided with a single phase winding, okay, that we have already seen. And the second one is a centrifugal switch is used in some types of motors in order to cut out winding used only for starting purpose. So in the construction we have seen there are two windings are there, starting windings and running winding. So whenever these two windings are used, in that case we have to cut starting winding from the system using centrifugal switch. So this is available in a single phase induction motor. It is not the case in a three phase induction motor. Now it has a distributed stator windings and squirrel cage rotor that we have already seen. When fed from a single phase supply, its stator winding produces flux, which is only alternating. It means one which alternates along one space axis only. It is not a synchronously revolving or rotating flux, as in the case of two or three phase stator winding fed from a two or three phase supply. See, in a three phase induction motor we know that there is a revolving magnetic field, but in this case there is no revolving magnetic fields because single phase is there. So how the winding is produces how the flux is produces we will see in this video next. Now an alternating or pulsating flux acting on a stationary squirrel cage rotor cannot produce rotation. Only revolving flux can produce rotation. So that is why single phase motor is not self starting, that we have already seen. Okay. So however, if the rotor of such a machine is given an initial start by hand or small motor or otherwise in either direction, then immediately the torque arises and the motor accelerates to its final speed. So this is the way how we can start the single phase induction motor. We have to do some external arrangement for the starting of the induction motor. This particular behavior of the motor has been explained in two ways. One is by two field or double field revolving theory, and another one is by cross field theory. So now we will see the double field revolving theory. Now this theory makes use of the idea that an alternating uniaxial quantity can be represented by two oppositely rotating vectors of half magnitude. So this is the method we are going to use. We can use two oppositely rotating vectors of half magnitude. According to alternating sinusoidal flux can be represented by two revolving fluxes, each equal to half the value of the alternating flux and each rotating synchronously in opposite direction. So this is the way how can we represent this single phase flux. For example, a flux given by phi is equal to phi m cos 2 pi f t is equivalent to two fluxes revolving opposite directions, each with a magnitude of 1 by 2 into phi m. It means half the magnitude and the angular velocity of 2 pi f. It may be noted that Euler's expressions for cos theta provides interesting justification for the decomposition of a pulsating flux. So here is some mathematical formula. From this we can see how we can decompose the flux. So one formula is cos theta is equal to 1 by 2 e raised to j theta plus e raised to minus j theta. Okay, so the term e raised to j theta represents a vector rotated clockwise through an angle theta, whereas e raised to minus j theta represents rotation in anti-clockwise. So this one is the vector and represented its direction through its sign. Now the above given flux can be expressed as phi is equal to phi m cos 2 pi f t. It means it is equal to phi m by 2 e raised to j 2 pi f t plus e raised to minus j 2 pi f t. So this way we can decompose the vector. Now here is how we can produce double field revolving theory. The right hand expression represents two oppositely rotating vectors of half magnitude. So here we can see here is A and B are the magnitudes. Its value is phi m by 2 and phi m by 2. And here through this arrow we can see the direction of these both vectors are in different. It means if the vector A is revolving in anti-clockwise and B is revolving in clockwise direction. Okay, so let the alternating flux have a maximum value phi m. Maximum value is phi m. Its component fluxes A and B will each be equal to phi m by 2, revolving anti-clockwise and clockwise directions respectively, that we have seen in this figure. Thus the resultant flux is phi r is equal to 2 into phi m by 2. It is equal to phi m. So this way we can find resultant flux. After some time, when A and B would have rotated through angle plus theta and minus theta, as in figure B, the resultant flux would be, first we will see how the angle is there. Yes, here we can see A is rotating in anti-clockwise to plus theta and vector B is rotating clockwise up to minus theta. So now we have to find the resultant of these two. Okay, so it will be equal to phi m cos theta. Resultant flux would be 2 into phi m by 2 into cos 2 theta by 2. It means it is equal to cos phi m cos theta. Okay, so phi m cos theta is the resultant of vector A and B for the case B. Now next, after a quarter cycle of rotation, fluxes A and B will be oppositely directed as shown in figure C. See in this figure, now here vector A and vector B and both are in oppositely direction, and magnitude of both of these are phi m by 2 and phi m by 2. So what will be the resultant? Simple, its resultant will be 0 because both A and B are in the opposite directions, and the value of both vectors are also phi m by 2 and phi m by 2. So resultant will be 0 for this case. so that the resultant flux phi r is equal to phi m by 2 minus phi m by 2 is equal to 0. Okay, so its output will be 0. After half a cycle, fluxes A and B will have a resultant of phi r is equal to minus 2 into phi m by 2 is equal to minus phi m. That we will see in this figure also. Okay, here we can see in figure D, A and B are in the left hand side, and it is just opposite of figure A. It means in figure A there is a resultant flux of plus phi m, then it is exactly opposite of position of figure A. It means its resultant should be minus phi m. So this way we can find this. Okay, phi r is equal to minus 2 into phi m by 2, it is equal to minus phi m. After 3 quarters of cycle, again the resultant flux phi r is equal to phi m by 2 minus phi m by 2, it is equal to 0 as shown in figure E. Okay, so again in this figure also the both the vectors are in the opposite directions and value of both the vectors are phi m by 2. So resultant of this figure is also 0, and this sequence will repeat after this. So these are the case how the flux is produces. If we plot the values of resultant flux against theta between limits theta is equal to 0 degree to theta is equal to 360 degree, then a curve similar to the one shown in figure is obtained. That is why an alternating flux can be looked upon as composed of two revolving fluxes, each of half the value and revolving synchronously in opposite direction. See, in this figure we can see the graph of a flux, and value is in between 0 to 360 degree. So how the flux is resultant flux is varying is seen in this case for 0 degree, 90 degree, 180 degree, 270 and 360 degree. So this is the way how can we represent the flux. Now it may be noted that the slip of the rotor is S, means S is equal to ns minus n upon ns. So this formula is same as a three-phase induction motor. Okay, so from this we can find, if we rearrange, then we can say that it is equal to 1 minus n upon ns, or n upon ns is equal to 1 minus s. Okay, so with respect to the forward rotating flux, it means one which rotates in the same direction as rotor, then its slip with respect to the backward rotating flux is 2 minus s. So what is the slip for backward rotating torque? SB is equal to, see, backward it means if the clockwise is taken as a forward, then backward will be anti-clockwise. So it is equal to ns minus n upon n. So it will be 1 plus ns upon s. By rearranging we can say that it is equal to 1 plus 1 minus s. So it is equal to 2 minus s. Each of the two components fluxes while revolving round the stator cuts the rotor, induces an EMF, and this will produce its own torque. See, we have seen two components, component A and component B. Okay, so these two components will cuts the rotor flux and induces their own EMF. It means due to flux A there is a EMF, and due to flux B there is also one EMF, and due to this there is a oven torques. It means it may be forward and backward torques. Okay, and both are oppositely directed, so that the net or resultant torques is equal to their difference. So this one is, we can see in a diagram of torque versus slip. So here we can see the in a clockwise direction and in a anti-clockwise direction how the torque is produces. So actually these two are the exactly opposite to each other. If one is in the clockwise direction, so another one is in the anti-clockwise direction, and amplitude of A is 5m by 2, then amplitude of B is also 5m by 2. So two oppositely torques are there in a single phase. Now the above figure shows both torques and the resultant torque for slips between 0 and +2. So here we can see the slip will be, here is 0 and slip here is 2. Okay. At standstill S is equal to 1. What is meaning of standstill? Whenever the speed is 0, we can call it as a standstill. So at standstill S is equal to 1 and 2 minus S is equal to 1. Hence TF and TB are numerically equal, but being oppositely directed produced no resultant torque. That explains why is no starting torque in the single phase motor. See what will happen. TF means forward torque and TB means backward torque, and numerical value of both torques are also equal, but its direction are in oppositely. So this is why there is no starting torque in the single phase induction motor. So we can say that a single phase induction motor is not self-starting. However, if the rotor is started somewhat, say in the clockwise direction, the clockwise torque starts increasing, and at the same time the anti-clockwise torque starts decreasing. So hence there is a certain amount of net torque in the clockwise direction which accelerates the motor to full speed. So this is the case when the external force is given in any direction, then at that direction the motor will run. The resultant torque of the single motor is 0 only at a slip of unity of the synchronous speed in either direction. Once rotated in either direction, therefore the single phase motor will continue to rotate in that direction, because the resultant net torque is produced to that left or the right of the standstill point. Here we can see this center is the standstill point. Okay, so if in this direction, then it will, if we move the motor in this direction, then it will rotate in clockwise. If we move in this direction, then it will move the motor in the anti-clockwise direction. So this is all about double field revolving theory. Thank you.